The title of this module is Paths and Circuits. To learn about paths and circuits, first we need to know about walks, trails and cycles. So clearly now we are going to discuss these things one by one. Let us now move on to the course. First, let us see the definition of the walk. For a graph G with vertex set V and edge set E, a walk is defined as a sequence of alternating vertices and edges such as V0, E1, V1, E2, so on up to EK, VK, where each edge EI given by Vi minus 1 Vi, the length of the walk is K. Let us now see some examples to understand walks better. So behind me on this board, we have a 5 vertex graph to explain how walks can be done. Now there are two kinds of walks. So in a walk, when you are taking in a very clear headed manner, you have a certain destination in mind and you keep on moving towards the destination. But sometimes when you are not clear headed, you tend to run around in circles. So a walk can be both clear headed and not very clear headed. So that is a way to understand walks. So first one, in this graph you can see there are 5 vertices A, B, C, D and E. The first walk is from AB, BC and DB. So AB, BC, CD and then DB. So the walk seems a little bit clear headed. Someone is going from here to here to here and then finally going to B. There is still a repetition of edges but not very confused form of a walk. But the next one, let us see this one, AB, BC and then CD, DC going back again. So DC and then CB and BC again coming back here, BC and then finally CE. This is also a walk. So plenty of repetition of edges. You are doing a very highly repetitive form of walking here, and this is also a walk. So this walk can be sometimes done when you are not clear headed and you are simply repeating the edges again and again. So this kind of walk is allowed. So a walk is where you can simply not have any destination in mind and still keep on doing it. So this is an example of a walk. Now let us see an example of open and closed walk. An open walk is when the starting vertex and the end vertex are not the same. So you start at one point and you reach somewhere else. The beginning point and the destination are not the same. But a closed walk is when you have the starting point and the ending point to be the same. Next we shall see about the two types of walks, namely the open and closed walk. So an open walk is when the beginning point and the destination are not the same, they need not be the same. In a closed walk, they have to be the same. So you start at one point, you end at the very same point. That is said to be a closed walk. Now we shall see an example here, and you can see that I have highlighted a certain walk in red color. So the closed walk here is CE, EG, GF and finally FC. You can see that we started at C and ended at C, and therefore this is an example of a closed walk. Next we shall see the definition of a trail. So you can see that in a trail no edges are repeated. In a walk you can repeat edges as many times as possible, but in a trail you should not repeat an edge even once. So in this graph you can see that A, B, C is an example of a trail. You can see that there is no repetition of any edges, but in certain graphs sometimes you cannot form a trail. Let us see this example. There is a trail here. No matter how much you try to draw a trail, you cannot form a trail in this highlighted part, I mean the red highlighted part. So even if I start from H, G, GF, FD, DC and then CB, which means that I am leaving out GC. So if I am going to take a trail from starting from H to B, I just have to repeat the at least one edge. I have to repeat it and only then I can create a walk. So which means that no trail can be formed in this red highlighted area. But in the other area also, can you form a trail? H, F, H, A and then A, B, again you are left with this part A, G. So in this graph you cannot form a trail at all. All you can have is a walk. Next we shall see an example now. Now the path which is highlighted here in red, so we do not know if it is a path yet, but let me call it a path. You can check whether if it is actually a path. So A, B, B, C, C, D, D, E, we are fine till here, but from E you have to go up to C, which means that the vertex C is repeated. So for this given set of vertices, can we create a proper path? No, the answer is no, because you have a repeated vertex C here. So in this graph we do not have a path with these vertices, but look at the vertices which are highlighted, the edges which are highlighted in black. So here you have A, F, F, C, C, G and G, D. Is this a path? Yes, it is a path, because no vertices are repeated. And can you find out the length of the path? It is AF1, FC1, CG1, GD1. So it is a path of length 4. So all graphs have a path, but when you are given a constraint as to you have to create a path within a certain number of vertices, sometimes the path might not materialize. Now we shall go on to the next definition, namely the cycle. The cycle is said to be a closed trail with no vertices being repeated here. And in this graph you can see the cycle being highlighted in red here. So BC, CG, GF and then FB. You might wonder that B is said to be the vertex which is repeated again. So we started with B and we ended with B, but we just said the definition should have no vertex repetition. So why are we repeating a vertex? So when we talk about the definition of a cycle, repetition of the initial and the final vertex is allowed, because a cycle is actually a closed structure. Therefore the starting and the ending point will be the same. That vertex repetition is allowed. In between you should not repeat any vertices. So that is the definition of a cycle, and therefore B, C, C, G, G, F, F, B, you can see that no other vertex is repeated, and therefore this is an example of a cycle. We shall see a circuit definition. A circuit is said to be a closed trail with repeated vertices. Now when you see cycle, there are no repeated vertices, but in a circuit you have repeated vertices. You can see the example behind me here. I have highlighted the circuit in red, and therefore if you start at H, you can start at any vertex for that matter, but I am starting at H, and therefore HB, BC, CF, FE, ED, DC, then CG and GH. You can see that the vertex C is repeated at least 2 times, and therefore you have a repetition of the vertex, but still this is a circuit. It might not be a cycle, but it is a circuit. So this is the example of a circuit, and I am sure that the definitions are now clear. Let us now do a small revision of how we have understood these things, and therefore let us see. A walk is where the vertices are repeated and the edges are repeated. A trail is where the vertices are repeated but the edges are not repeated, but it is open ended, which means that the starting point and the ending point are not the same. That is the meaning of saying open. Next we see circuit. Vertices are repeated but edges are not repeated, and it is closed. Closed means the starting and the ending are the same. Path, the vertices are not repeated, edges are also not repeated, but it is open ended, which means the starting and the ending points are not the same, they are very different. And cycle, here vertices are not repeated, edges are not repeated, and it is closed. The starting and the ending points are the same. So you can keep this table in mind in order to understand the definition of walk, trail, circuit, path and cycle. I hope things are clear now. In the previous section, we saw in detail about the circuit, the cycle and the various other definitions. So we will be seeing something called the Eulerian circuit and the Hamiltonian cycle, and these definitions we will be studying in detail in the upcoming modules, especially the next 2 modules. So let us now concentrate on something called the Euler path, and we will see some of the applications of the Euler path for now. The application of Euler path. In 1736, Leonhard Euler was puzzled whether it is possible to walk across all the bridges on the river Pregel in Königsberg only once. and return to the starting point. You can see the figure given in the screen. This is how Euler stated the problem in Solutio Problematis ad Geometriam Cetus Pertinentis. In 1736, this paper was published and the English translation can be found in Biggs et al. In 1976. In Königsberg in Prussia, there is an island A called Neiphof. The river Pregel, which surrounds it, is divided into two branches as can be seen in the picture displayed on the screen. And these two branches are crossed by 7 bridges A, B, C, D, E and F along with G. Concerning these bridges, it was asked whether anyone could arrange a route in such a way that he would cross each bridge once and only once. I was told that some people asserted that this was impossible, while others were in doubt, but nobody would actually assert that it could be done. On the basis of the above, I have formulated the general problem given any configuration of the river and the branches into which it may divide, as well as any number of bridges, to determine whether or not it is possible to cross each bridge exactly once. In order to solve this problem, Euler, in an ingenious way, abstracted the bridges and the land masses. He replaced each landmass by a dot called the vertex and each bridge by an arch called an edge or a line. Euler proved that there is no solution to this problem. The Königsberg bridge problem was the first problem studied in what is later called the graph theory. The bridges of Königsberg problem is really a question about the existence of Euler paths. There will be a route that crosses every bridge exactly once if and only if the graph given has an Euler path. You can see the graph displayed on the screen and you can see that it is a multi-graph, meaning that there are more than one arch connecting every two pair of vertices. The graph is small enough that we could actually check every possible walk that does not reuse edges, and in doing so we can convince ourselves that there is no Euler path, let alone an Euler circuit. On small graphs which do have an Euler path, it is usually not difficult to find one. Our goal is to find a quick way to check whether a certain graph has an Euler path or circuit, even if the graph is quite large. We have already seen that paths and cycles are certain kinds of walks and subgraphs in graphs. These terms are also used to describe certain types of graphs. If the vertices of a graph G of order n can be labelled or relabelled as V1, V2, so on up to Vn, so that its edges are V1, V2, V2, V3, so on up to Vn minus 1 Vn, then G is called a path. While if the vertices of a graph G of order n greater than or equal to 3 can be labelled or relabelled as V1, V2, so on up to Vn, and so that its edges are labelled as V1, V2, V2, V3, so on up to Vn minus 1 Vn and V1, Vn, then G is called a cycle. So, V1, Vn means they are forming a closed path. A graph that is a path of order n is denoted by Pn, while a graph that is a cycle of order n greater than or equal to 3 is denoted by Cn. Several paths and cycles are shown in the figure given on the screen. Based on these definitions we have seen before, let us discuss a theorem. If a graph G contains a UV walk of length L, then G contains a UV path of length at most L. Let us see the proof now. Among all U to V walks in G, let P be equal to U equal to U0, U1, so on up to Ui minus 1, Ui, Uj, Uj plus 1, so on up to Uk, and Uk being the vertex V. So, this is a UV walk and this is a UV walk of the smallest length, say k. Therefore, k is said to be less than or equal to L. We claim that P is a UV path. Assume to the contrary that this is not the case, then some vertex of G must be repeated in P, say ui is equal to uj for some I and j with 0 less than or equal to I less than j less than or equal to k. If we then delete some vertices ui plus 1, ui plus 2 so on up to uj from the path P, we arrive at the UV walk. The result says that common graphs in two families A is equal to paths and B is equal to cycles, where A represents a set of paths and B represents a set of cycles. Then A intersection B is equal to empty. The proof is, in a cycle the number of vertices and the edges are equal, but this is false for a path. Let us see the next result. A graph in which every vertex has degree 3 has no decomposition into paths with at least 5 vertices each. The proof for this is, suppose that G has such a decomposition. So, we are going proof by contradiction. Since every vertex has a degree 3, each vertex is an endpoint of at least one of the paths and is an internal vertex on at most one of them. Since every path in the decomposition has 2 endpoints and has at least 3 internal vertices, we conclude that the number of paths in the decomposition is at least n of g by 2 and is at most n of g by 3, which is impossible. Alternatively, let k be the number of paths. There are 2k endpoints of paths. On the other hand, since each internal vertex on a path in the decomposition must be an endpoint of some other path in the decomposition, there must be at least 3k endpoints of paths. The contradiction implies that there cannot be such a decomposition. The next theorem is, each UV walk contains a UV path. The proof: we use ordinary induction on the length L of the walk, proving the statement for all pairs of vertices. A UV walk of length 1 is a UV path of length 1. This provides the basis. For the induction step, suppose L is greater than 1 and let W be a UV walk of length L. By induction hypothesis, the walks of length less than L contain paths linking their endpoints. If U is equal to V, the desired path has length 0. If U is not equal to V, let WV be the last edge of W and W dash be the UW walk obtained by deleting WV from W. Since W dash has length L minus 1, the induction hypothesis guarantees a UW path P in W dash. If W is equal to V, then P is a desired UV path. If W is not equal to V and V is not on P, then we extend P by the edge WV to obtain a UV path. If W is not equal to V and V is on P, then P contains a UV path. In each case, the edges of the UV path we construct all belong to W. We shall see one more theorem. The union of the edge sets of distinct UV paths contain a cycle. The proof: again we use induction on the sum L of the lengths of the two paths for all vertex pairs simultaneously. If P and Q are UV paths, then L is greater than or equal to 2. If L is equal to 2, then we have distinct edges consisting of U and V, and together they form a cycle of length 2. For the induction step, suppose that L is greater than 2. If P and Q have no common internal vertices, then their union is a cycle. If P and Q have a common internal vertex W, then let P dash, P double dash be the UW subpath of P and the WV subpath of P. Similarly, define Q dash, Q double dash. Then P dash, Q dash are UW paths with total length less than L. Similarly, P double dash, Q double dash are WV paths with total length less than L. Since P and Q are distinct, we must have P dash and Q dash as distinct, or P double dashed and Q double dashed as distinct. We can apply the induction hypothesis to the pair, that is a pair of distinct paths joining the same endpoints. This pair contains the edges of the cycle by the induction hypothesis, which in turn is contained in the union of P and Q. Next we shall see a remark. The union of distinct UV walks need not contain a cycle. Let G be equal to P3 with vertices U, X, V in order. The distinct UV walks with vertex lists U, X, U, X, V and U, X, V, X, V do not contain a cycle in their union. Next we shall see a theorem. If W is a non-trivial closed walk that does not contain a cycle, then some edge of W occurs twice in succession, once in each direction. The proof is given by induction on the length L of W. We are given L greater than or equal to 1. A closed walk of length 1 is a loop which is a cycle. Thus, we may assume that L is greater than or equal to 2. The basis step is L is equal to 2. Since it contains no cycle, the walk must take a step and return immediately on the same edge. For induction step L greater than 2, if there is no vertex repetition other than first vertex is equal to the last vertex, then W traverses a cycle which is forbidden. Hence, there is some other vertex repetition. Let W dash be the portion of W between the instances of such a repetition. The walk W dashed is a shorter closed walk than W and contains no cycle since W has none. But the induction hypothesis W dash has an edge repeating twice in succession, and this repetition also appears in W. In this module, we have seen about walks, trails and cycles with examples, and then we moved on to paths and circuits with some properties. I hope that this module was useful for you to understand some of the basic definitions of graph theory. Let us meet in the next session. Thank you.